Hey everybody, it's Dr. Morgan. Welcome back to astronomy. Last time we talked about the fact that we did not even really know there were other galaxies, or rather, we did not know that some of the fuzzy little blobs we see in our telescope are completely separate galaxies from the Milky Way until about 100 years ago. A little less than 100 years ago, the late 1920s or so. So it's fairly remarkable that in the past century, our understanding of how big the universe is has increased by a factor of 1,000,000. From thinking that the stars we see in the sky that make up the Milky Way galaxy are the whole universe, to understanding there are billions of those galaxies scattered throughout the universe. The type of galaxy we kind of probably think of, if you think of anything when you think of a galaxy, is this kind of spiral galaxy. This is the Andromeda galaxy. It's the closest bright galaxy, or the closest big galaxy to the Milky Way. And I think we've probably looked at pictures of Andromeda before and talked about it. You can actually see the Andromeda galaxy with your naked eye. If you go someplace very, very, very dark where you can see the Milky Way and you know where to look for it, you can see it as a fuzzy little oval on the constellation of Andromeda. The features of spiral galaxies are that they are flat. The stars orbit largely in a plane, although they do have a halo of stars that don't show up in photographs like this. And the plane of the galaxy is also filled with gas and dust. These dark areas you see are not just places where there are no stars, they're places where gas and dust are opaque enough to block our view of the stars in those regions of the galaxy. And the density of stars increases as you get to the center. The density of stars at the center of a spiral galaxy is not as bright as it looks, not as dense as it looks in photographs like this. Photographs like this are exposed so that you see the whole galaxy, and the edges of the galaxy are dimmer. So when we take a photo of a galaxy like this, we overexpose the center and make it look brighter than it actually is. It's kind of a photographic trade-off. So, it looks like the stars in the center of a galaxy, they're so close, they're practically touching. They're not. They're still a light year or so apart. But they are more dense in the center than they are at the edges. This is a kind of spiral called a barred spiral, B-A-R-R-E-D, named after this bar, this sort of rectangular structure connecting the spiral arms on one side to the spiral arms on the other side. There's some evidence that our Milky Way galaxy is maybe a barred spiral. It's hard to tell from the inside, right? We talked about the fact that we can't see our whole galaxy because we are in the middle of the galaxy. So figuring out its overall shape and the overall shape of the spiral arms is fairly complicated. But there's quite a bit of evidence that the Milky Way may be a barred spiral that looks sort of like this. There are spiral galaxies with kind of loosely wound spiral arms, and there are spiral galaxies with very tightly wound spiral arms. You can look at this galaxy and you see the difference in color between the central regions and the spiral arms. What do those differences in color mean? Well, they mean there's different kinds of stars there, right? In the center, there are, it looks like yellow and orange and red stars. And in the arms of the galaxy, it looks like there are more blue and bluish white stars. That makes sense if you think about what we said about the Hertzsprung-Russell diagram. It goes from hot stars that are blue, bluish white, to medium temperature stars, AF and M stars, or sorry, AF and G stars like our sun, that are kind of yellow or yellowish white, and then older stars. So what we can guess from just looking at this galaxy is that the spiral arms have younger stars, because those O and B type blue stars burn themselves out very quickly, and the galactic core has older stars, older main sequence stars like the sun, and stars that are even cooler than the sun, maybe K and M stars as well. So just looking at the population of stars in a galaxy, we can see that they're different. We have some galaxies that have a very, very tightly wound spiral arm. This galaxy in particular has a ring of very bright bluish white stars, which suggests a great deal of rapid star formation is happening in that place in the galaxy, right? If bluish white stars are fast burning, that means if we see them, they are young. And this is a ring of recent star formation in this galaxy. Mostly we're just looking at pretty pictures right now. Again, spiral galaxies can sometimes have very loosely wound arms. sometimes we see them on the edge, and we can really see that central disk of the galaxy, where the spiral arms are, is heavily populated with opaque gas and dust. And it's this gas and dust out of which stars form. Okay, this is, I think, the Sombrero Galaxy, maybe the constellation of Virgo. I don't have every one of these memorized, and they're not all labeled. You can see a very diffuse core in this galaxy, very tightly wound spiral arms, and a great deal of dust and gas in the spiral arms of that galaxy. Galaxies interact with one another, and they have gravitational pulls. And if they're two galaxies close to one another, they can exert a gravitational pull on one another. This is a spiral galaxy that's actually been kind of twisted by a gravitational interaction with another galaxy. So spiral galaxies aren't always perfectly flat. It's worth talking about just really quickly the dynamics of spiral arms in a spiral galaxy. The stars in a galaxy are orbiting the mass of the whole galaxy. The closer you are to the center, the faster you orbit, the further out to the edge, the slower you orbit. Because of this, if you started out a spiral arm in a galaxy and all the stars in that spiral arm moved around in their orbits, the ones in the center would move fast and the ones on the edge would move slow, and the spiral arms would gradually wind themselves up so that after just a few 100 million years, because the stars way out on the edge take 300 million years to go around, and the stars in the middle only take 50,000 years to go around, spiral arms will kind of wind themselves up after less than 1 billion years. But we don't see that. We see galaxies with these loose spiral arms that are not wound up by the rotation of the stars. So it requires a little bit of explaining. And the way to think about the spiral arms of a galaxy is not as a static structure made of the same stars moving around in spiral arms. A spiral arm of a spiral galaxy is more like a traffic jam. It is a region of increased density that has a persistent shape. But it's not always the same stars living in that spiral arm. If you watch this animation of a spiral arm, you can see stars being born, turning on, and other stars dying and winking off. The spiral arms, it's probably too fuzzy for you to see at your screen resolution, but if you look at an individual star, it doesn't stay in one place in the spiral arm. It actually moves over time. What happens is that new stars are born at the edge of the spiral arm where matter is the densest. So think about a traffic jam. Okay, there's an accident by the side of the road, causes a traffic jam. The cars get moved off to the side of the road, but the traffic jam persists for a while because people were already stopped, and all the cars can't start moving at once. And people slow down to look at the accident on the side of the road and stuff. That traffic jam on, say, I-95 could last for an hour. Those same cars are not in that traffic jam for an hour. Right? There are always cars leaving the front of the traffic jam as they pass by the accident, and there are always new cars entering the back of the traffic jam because it hasn't started completely moving yet. So a traffic jam that lasts for an hour is not a structure made of the same 500 cars for that whole hour. There are always cars leaving the front of this traffic jam, and there are always new cars entering the back of the traffic jam. A spiral arm is like that. There are always new stars being formed at the edge of the spiral arm, and there are always stars kind of wandering out of the back end of the spiral arm, being left behind as the spiral arm rotates. So a spiral arm is a dynamic structure that is not always made of the same stars. And that's how it can persist for billions of years because it is self-sustaining. It's always creating new stars on its edge. The other most common type of galaxy is the elliptical galaxy. Elliptical galaxies are not as pretty or interesting looking as spiral galaxies. They are football or watermelon shaped blobs of stars that are elliptical in all three of their dimensions. They don't have a very well concentrated core. They're kind of uniform, more uniformly distributed. They can be almost spherical, as in this example, and they can be highly elongated, as in this example. Elliptical galaxies are often bigger than spiral galaxies and have more stars, especially what's called giant elliptical galaxies. A spiral galaxy can have anywhere between a couple hundred, like 200 billion stars, like the Milky Way, up to maybe 500, 600, 700 billion stars. There are some giant elliptical galaxies with 1 trillion stars. That's 1,000 billion stars. This is an elliptical galaxy that has some gas and dust that we don't usually associate with elliptical galaxies. Elliptical galaxies are mostly, they've kind of used up all their gas and dust in the process of star formation. We think what happened here is an elliptical galaxy gobbled up a spiral galaxy and basically ripped it to shreds, and this gas and dust is the gas and dust left over from that spiral galaxy that was subsumed into the elliptical galaxy by its gravitational pull. There are also little tiny elliptical galaxies. When we look at a picture of this big spiral galaxy in Andromeda, M31, it has a little friend that orbits around it, which is a dwarf elliptical galaxy. Galaxies can orbit one another just like moons can orbit planets. Our Milky Way galaxy has at least 2 satellite galaxies. You can't see them from the northern hemisphere. You have to go to the southern hemisphere. And if the Milky Way looks like a stripe of light that goes all the way across the sky, these look like little disconnected blobs of light in the sky. We call them the Small Magellanic Cloud and the Large Magellanic Cloud. Those aren't very exciting names, actually named after Magellan, European explorer who was the first Western European person to see them. Obviously, the people who already lived in the southern hemisphere had known about these things for centuries. But historically, a lot of what happened in centuries around the scientific revolution is that people from Europe just traveled around the world naming stuff after themselves. So we're still stuck with that name, the Small Magellanic Cloud and the Large Magellanic Cloud. The small and large Magellanic Clouds are dwarf irregular galaxies, which we'll see in a minute, that orbit around the Milky Way. So the Milky Way is a galaxy of hundreds of billions of stars that has 2 satellite galaxies that actually orbit around it. It actually might have more, but they're on the other side of the galaxy, blocked by the galaxy, so we can't see them. Giant elliptical galaxies can be as big as 5 million light years across. That's about 50 times bigger than our galaxy, and can have more than 1 trillion stars. So here's our whole Milky Way galaxy, how big it would be next to a giant elliptical galaxy. So they can be really, truly enormous and massive and very, very bright. This is I'm going to breeze by this really quickly. This is a classification scheme developed by Edwin Hubble just to describe the shape of galaxies, from elliptical galaxies to spiral galaxies, elliptical galaxies from very round ones, which are E0s, to very long ellipses, which are E7s, and spiral galaxies from very tight spiral arms, which are A-type, to very loose spiral arms, which are C-type, and then divided from spirals into barred spirals. It doesn't really mean anything. We talked about the HR diagram, Hertzsprung-Russell diagram. We said if you take the properties of stars and you plot them out and you group them according to their brightness and their temperature, that those groupings mean something. And they tell us something about how stars evolve and change over their lifetimes. I think Hubble had the idea that maybe galaxies evolve and change from one type to another the way stars can evolve and change from one type to another. That doesn't seem to be true. So this classification scheme, we still use it. We will still say such and such a galaxy is an SB spiral, but it's just a label describing that it's a spiral and its arms are tightly wound. It mean anything about the history or the evolution or the structure of the galaxy. So you don't need to remember anything about the tuning fork diagram. It's just in here because it's of historical interest, because Hubble's the person who figured out that other galaxies were galaxies. One interesting distinction to make when we see astronomical pictures and there's just a whole bunch of stars that make a blob of a whole bunch of stars. What do we call that thing? And at one end, we have just star clusters. Star clusters are within a galaxy, usually. And they can have anywhere between hundreds of stars to thousands of stars. Maybe a very big globular cluster might have millions of stars. A galaxy, however, usually has billions of stars, if not hundreds of billions of stars. So a galaxy is a bigger and much more populated mass of stars in a star cluster. Our own Milky Way galaxy has star clusters within it, but they're much, much smaller than an honest to goodness galaxy. And somewhere in the edges, there might be some overlap. There might be some blob of stars orbiting a galaxy that has, let's say 200 million stars. Is that blob of stars with 200 million stars a really big star cluster, or is it a really small galaxy? Those are just arbitrary distinctions, just like the distinction between planet and dwarf planet as an arbitrary distinction. One thing that we are interested in is why spiral galaxies and elliptical galaxies are so different from one another, why they look different from one another, in terms of their symmetry, in terms of the amount of gas and dust, etc. This is not something we have fully figured out, but I'll give you one model that explains why maybe elliptical galaxies and spiral galaxies are different. If you've got this giant cloud of gas and dust that existed 13 billion years ago, shortly after the Big Bang, and that gas cloud is dense, and as it starts to collapse, it gets dense enough for stars to start forming while it's collapsing. They will start orbiting the center in all different directions, and that blob of gas doesn't really have any axis of symmetry, and that becomes an elliptical galaxy. So if star formation begins quickly while this cloud is still collapsing and before it begins to rotate very fast, you will get an elliptical galaxy. But if the cloud is a little less dense, as it starts collapsing, it will start rotating. Conservation of angular momentum, same reason an ice skater rotates faster when they pull in their arms. If it starts to rotate, it will flatten like a pizza dough thrown up in the air. If it starts to rotate and flatten first before the stars start to form, then all the stars will form in that flat disk. So if star formation doesn't begin until the cloud has begun to spin and rotate and flatten, because the density of the cloud wasn't high enough to form stars yet, and the stars form in that flattened rotating disk, then you wind up with a spiral galaxy. Okay? So the difference between spirals and ellipticals is, when did the stars start to form? Did they start to form when the gas cloud was big, before it had started spinning very much? If so, those stars will wind up in an elliptical galaxy at the end. If they started forming after the cloud had already collapsed and flattened and started spinning rapidly, those stars will form in a spiral galaxy. There are, however, other explanations for what might create spiral galaxies. For example, if you have two elliptical galaxies that are orbiting one another, the gravitational pull of one of those galaxies can pull the shape of the larger galaxy into a spiral. We see examples of places where it looks like two galaxies are gravitationally interacting with one another. So it may be that the spiral shape of this galaxy is caused by its interaction with, that smaller galaxy. Here we see two spiral galaxies that are actually colliding with one another. Another example. So another thing that might happen over time is spiral galaxies can merge together. And there's another theory for the formation of elliptical galaxies, which is that all elliptical galaxies are created by the merger of spiral galaxies that over time wind up destroying the spiral structure of the galaxy. So here's a computer simulation of a spiral galaxy colliding with another spiral galaxy, and it really messes up the structure of those galaxies first, you wind up with these spirals with these long tails. But since that distorts the orbits of all of the stars, what you eventually wind up with at the end is this mixed together blob of stars where there's no more axis of symmetry anymore. By the way, when two galaxies collide with one another, remember, stars have light years of space in between them. The stars in the galaxy don't actually collide. It's more like two flocks of birds flying through one another, right? Two flocks of birds can fly through one another and without any birds crashing into one another, because there's 2 or 3 birds worth of space between every bird. So there's plenty of room for the stars in two galaxies to merge together. Finally, it's barely worth mentioning that there are these things called irregular galaxies, which, as you might suggest, are neither spiral nor elliptical. They are just irregular blobs of stars, usually smaller than spirals and ellipticals, and sometimes kind of treading that line between a big star cluster and a small galaxy. There are also galaxies where weird stuff is going on. There are galaxies that are colliding with one another. There are places that it looks like an elliptical galaxy is passing right through a spiral galaxy. There are ring galaxies, which we think happen if a elliptical galaxy crashes into a spiral galaxy head on, almost like dropping a rock in a pond, and you get this burst of star formation in a ring. The crazy thing about this picture is if you look at this ring galaxy and look in the hole in the ring, there is another ring galaxy lined up with this one, another billion light years in the distance, which is a pretty crazy coincidence. And finally, there are what we call active galaxies. And we talked about this briefly when we talked about supermassive black holes. There are galaxies that when you look at them in visible light, they're just a spiral blob of stars. But when you look at them in other wavelengths, they're these huge jets of material that are being ejected through intergalactic space. And we think that what is going on in the center of that galaxy is a rapidly rotating black hole with a very energetic accretion disk that's creating this vortex of magnetic fields that shoots out electrically charged particles along the axis. As far as we can tell, every large galaxy we observe has got some kind of supermassive black hole in its center. Here's a galaxy. Again, it looks like one of these kind of collided elliptical and spiral galaxies. Here it is in visible light. Here it is with a radio image overlaid over top of it, of that same galaxy to the same scale. So you see these jets of material are being shot out through intergalactic space. And this distance is hundreds of thousands, if not millions of light years. So something very energetic and very tiny is going on in there at the center. And the only thing we can imagine that is that energetic and that tiny is material spiraling into a black hole. Here's a close-up of the centers of one of those galaxies, showing this jet of material being ejected from the magnetic north pole of the accretion disk. Again, it's not coming out of the black hole. Nothing can come out of a black hole. It's coming out of the highly energized stuff rapidly rotating and spiraling into the black hole at huge velocities. So that's all I'm going to say, I think, about that for right now. What I want to do next, what we're set up to do now, is to talk about one level of structure up. So galaxies are hundreds of billions of stars orbiting around one another. Great. What about galaxies and how they interact with one another? What about how galaxies are distributed in intergalactic space? What about the universe as a whole? That is where we're headed next.